Greetings. Welcome to Eaton's Launch and Learn, entitled Innovation in Power Distribution Substation Design. My name is Dave DeRocher with Eaton in Wilsonville, Oregon. Today I would like to share with you some of our experiences over the past 2 to 3 years in working towards a better and improved design in unit substations. Here is our agenda for today's session. I'd like to start off by first reviewing unit substation designs as they are applied today in both commercial and industrial applications. Then let's dig a little bit deeper and look at some weak spots in some of the traditional designs. And also, what has technology done? Has innovation helped shift power distribution design so that we can improve both safety and reliability of today's typical substation? And then towards the end, we'll do an economic evaluation and find out what does this new technology cost, and is there enough benefit there to shift our engineering thinking? Okay, so let's get started with some of the challenges in today's unit substation designs. We'll do the good, the bad, and the ugly. I'll have to apologize in advance. Clint Eastwood was one of my favorites in that movie. So we'll start off with the good on unit substations. What I've shown here is a typical configuration, most certainly the workhorse in most industrial and commercial applications, and there are thousands of these substations installed across North America. From left to right, we start off with a 15 kV metal enclosed primary fused load break switch. This assembly is manufactured typically to a metal enclosed standard ANSI C37.20.3. And as you can see, I've shown a 100E current limiting fuse for this 1500 kVA design. Next, let's move to the right to the transformer. The transformer could be either a dry type or liquid filled design. I've shown a dry type here. Substation transformers in this class are typically manufactured to ANSI C57.12. Typical impedance in this case 5.75%. Finally, through the turns ratio of the transformer, we typically transform down to a usable distribution voltage, 480/277 volts. And to the far right, we have a close-coupled piece of low-voltage metal enclosed switchgear. What I have shown here is switchgear utilizing low-voltage power circuit breakers that are typically in a draw-out configuration. This assembly is manufactured to UL 1558. The secondary switchgear could also be a switchboard configuration with group-mounted distribution utilizing molded case circuit breakers manufactured to the UL standard 891. Take note here that I've shown a vertical section connected directly to the transformer that includes main metering with a 2000 amp rated secondary bus, and then 4 feeder breakers with no secondary main, the feeders rated at 800 amperes apiece. So what do we see that's good in this assembly? Well, first off, it's fairly low cost, and also it's space efficient. Let's take a look at the bad next. You can see here that in this design we have some inherent limitations surrounding the secondary switchgear assembly. Off to the right, you can see I've listed that there really is no secondary bus fault protection, and also some issues with secondary bus overload protection. It's interesting that both of these issues can be traced back to the codes and standards under which we operate here in the U.S. In this case, I've referenced a couple of the sections from the 2008 National Electrical Code. First, at the lower left, NEC Article 240.21 discusses overcurrent protection. And it clearly states that the ampacity of the secondary conductors in this assembly shall not be less than the combined calculated loads on the circuits supplied. What this really means is that Eaton or any other manufacturer of this assembly could assemble a switchboard, in this case, or a piece of switch gear, with 4 800 amp feeders as I've shown here, and a 2000 amp rated bus. And if you do the math on this, you can see that I could have up to 3200 amps of load on this 2000 amp bus, clearly overloading the bus. So this article of the code clearly puts the onus on the user of the equipment to determine what the loading is and to size the bus and the feeders accordingly. The next code issue is the NEC Article 450.3 under Equipment, and this is specifically related to transformers and substations. Most of you are familiar with this. This is the classic 6-handle or 6-disconnect rule. And here the code says that where secondary overcurrent protection is required, the secondary overcurrent device shall be permitted to consist of not more than 6 circuit breakers or fuses grouped in one location, essentially eliminating the need for a secondary main breaker. I'd like to take a look now and really focus on the secondary bus in this assembly. First of all, let's assume that we had a bus fault. I'm showing here on the lower left a 10,000 amp secondary arcing fault between phase and ground on the secondary of this substation. Well, if we look at the next upstream protective device, it happens to be that 100 amp fuse on the primary of the sub. And at 13.8 kV, the 348 amps that would be reflected onto the primary of this substation would ultimately result in this fuse clearing in 160 seconds. 160 seconds in a fault condition is forever. In actual practice, we would likely expect this fault to propagate from a single phase into a 3-phase fault due to the ozone in the arcing, and the fuse would clear much faster. But in the interim, most of the low voltage bus would likely be laying on the floor of the low voltage switchgear assembly. And more importantly, if some worker were to be involved or engaged in this equipment during this fault condition, there would obviously be an arcing fault resulting in serious injury or even death. By now, most of us are already very familiar with the NFPA 70E, a standard for electrical safety in the workplace. This standard was recently updated in 2009, and there's some very clear requirements in this standard that focus on quantifying the risks for personnel working on this equipment live and actually putting up a label on the equipment telling operators what the hazard is in terms of the arc flash boundary, the calories per centimeter squared, and the required personal protective equipment, or PPE, so that someone working on or maintaining this equipment will clearly know the risks before they approach the equipment and perform work. I've shown below the NFPA 70E calculations for this specific substation that were performed at an industrial facility here in the Pacific Northwest in Oregon. And as you can see, in this specific situation, the symmetrical fault current was fairly high, about 32 kA, but the arcing fault current, the calories per centimeter squared, and the required PPE were all off the charts. This brings me to a focus on the low voltage secondary bus of the switchgear, what I've shown here in a purple color. I've called this the fault-free zone. I've heard this term used for this portion of the substation in the past. Truth be told, I don't know where that term came from. I think what it means, though, is that you don't ever want to have a fault in that portion of this substation, because if you do, you're really relying upon the next upstream protective device, in this case the fuse and the primary load break switch, to clear the fault, and frankly, it's not an adequate device to be able to do that. The intent of the fuse in the medium voltage switchgear assembly is to protect the transformer if there's a fault in that assembly. So how do we fix this problem? Only 2 ways I know of. One would be to add a overcurrent protective device, either a fuse or a secondary circuit breaker in the low voltage switchgear, or 2 would be to put some sort of protective device in the primary with current sensing in the secondary to be able to trip the primary in the event of a bus fault on the secondary assembly. Our new innovative substation design focuses on the latter of those 2. So before we get into the final answer, let's take a look at some technology changes that have allowed us to improve substation design. First off, let's take a look at how technology has influenced medium voltage vacuum circuit breakers. I've shown here photos of a pair of circuit breakers. They both have identical ratings, 15 kV, 1200 amperes, 40 kA interrupting. The one on the right is the traditional design that's been around for over 30 years, and the one on the left is a fairly new design. that's been around for about 3 years. As you can see, it's much smaller and lighter. It carries the same ANSI ratings, although not available in as high of interrupting or current ratings. And importantly, it also has a different feature in that there is a trip unit that is integral to the breaker itself, much like what you would see in a low voltage power circuit breaker. The trip unit works in conjunction with a linear trip actuator that allows the breaker to clear somewhat faster under fault condition, 3 cycles versus 5. And it also includes in this design a 2-step stored energy mechanism, similar again to a low voltage power circuit breaker. The one on the right, the traditional design, would use an external relay to clear a fault, and it also applies a 2-step stored energy type of mechanism. One other technology shift we'd like to look at is zone selective interlocking. Actually, this technology is not that new. It's been around for a number of years, and most circuit breakers and protective relays by manufacturers today include ZSI capabilities as standard. What I've shown here is a main breaker and 3 feeder breakers in a typical substation configuration. You would, for selective coordination, set up your main breaker with a longer short time delay. I've shown 0.5 seconds here. Then the feeder breakers, each shown with 0.2 seconds. So let's say we have a downstream fault from this substation. Downstream of one of the feeder breakers, I've shown a fault in the middle feeder at 0.1. In this case, the feeder breaker would time out its short time delay of 0.2 seconds and then clear the fault. The breaker nearest the fault cleared the fault, mission accomplished. But if I had a bus fault, which I've shown in item 2, now I have a situation where I'm waiting for the main breaker's short delay to time out, when in fact I know there's a fault on the bus. So to make sure the breaker knows there's a fault on the bus, we connect all breakers with what I've shown as a green control wire called ZSI. And in fact, if there is a bus fault, the primary breaker or main breaker would ask the feeders, "Do you see the fault?" They would all acknowledge no, and then the main breaker would trip instantaneously with no intentional delay. Ultimately, the benefit here, as I've shown below, is clearing the fault faster and reducing the arc flash hazard on the main bus. In this case, as I've shown below, reducing the arc flash hazard from over 40 calories per centimeter squared as defined in the NFPA 70E, greater than category 4 or unapproachable, to 7 calories per centimeter square or category 2 PPE, where a maintenance electrician could perhaps work on this equipment energized, performing a task like racking out a secondary breaker off of this bus in category 2 clothing, fire-rated shirt and pants. Finally, let's take a look at a third innovation area, an area surrounding technology and protective relaying itself. A number of the higher-end digital protective relays today will include multiple settings group capability, essentially allowing the operator to set one selective coordination curve for one situation and a second for another. Because of the lowering cost of electronics, this type of capability has now been embedded into some of the lower-end trip units and even in some integral trip units that are part of low voltage and medium voltage power circuit breakers. The Eaton offering here is called ARMS, Arc Flash Reduction Maintenance System. This actually is an option on low and medium voltage integral trip units for circuit breakers. And you can see in this picture that we have in the upper left-hand corner of the integral trip unit the capability of turning on a maintenance mode and selecting 5 different instantaneous settings. When I want to set the breaker or the tripping system up so that if someone was working in downstream energized equipment, the trip unit would react differently and in fact trip instantaneously. Obviously, the lower clearing times associated with an instantaneous trip will reduce the downstream arc flash energy. There also is a blue indicating light on the trip unit showing that the relay is set in the ARMS mode. Of course, a door-mounted switch and light can also be provided if required.